Okay. Good afternoon to everyone. A very warm welcome from my side. I am Paolo Bertofina, Marketing and Communication Specialist for EasyRain. I'm really glad to introduce the webinar held by EnginSoft and EasyRain on water spray parameters optimization using 3D CFD Particle Simulation for an automotive anti-aquaplaning system. The webinar has three speakers, myself, Michele Norelli for EnginSoft and Silvestro Chiriches for EasyRain. I will hand over to them in a few seconds, and they will discuss the collaboration between EasyRain and EnginSoft and all the technical details related the usage and the importance of Particleworks software when it comes to developing AIS system. So Michele and Silvestro, if you want to say hi to the audience.
Good afternoon also from my side, Michele speaking from EnginSoft, and I would like to, thanks you all for joining this webinar, and thanks EasyRain for the very interesting collaboration. My task today will be to guide you and introduce you Particleworks and the capabilities of this meshless approach for tire simulation or wading and soiling simulation. Silvestro.
Thank you, Michele. Thank you, Paolo. My name is Silvestro Chiriches, and I'm a mechanical engineer for EasyRain, and I'm in charge with the development of the AIS system from a mechanical and hydraulical point of view. I will present the technical results, and I will explain the collaboration with Particleworks.
Okay, so let's get into the webinar, starting off from the EasyRain perspective. My task in the following minutes will be to introduce EasyRain and its vision, giving an overview over the aquaplaning phenomena, and describing AIS anti-aquaplaning system. So EasyRain is a startup in the field of automotive safety on low grip condition, founded in 2013 by Giovanni Blandina. Over the years, EasyRain has grown, and his team is now including 15 people, including some of high-profile engineers from the automotive industry. EasyRain chairman is Eringer Schuring, who was CEO of Magneti Marelli Electronics, and Mauro Pieralini is EasyRain business developer, and he was a technical leader into Fiat Automotive Group, and has the task of developing the Alfa Romeo 4C. So when Giovanni first set up the company in 2013, he had the vision of saving lives and reducing road fatalities on dangerous wet road. He fulfilled and is fulfilling this vision by developing a new generation of active safety system, resulting in our current three-pillar ecosystem with AIS, the system we are discussing in this contest, EDP platform, EasyRain digital platform for virtual sensor for road detection, and ERC, EasyRain Cloud, for cloud computing to enhance the performance of AIS and EDP systems. As I mentioned before, aquaplaning and wet road condition are the EasyRain vision. I mean, EasyRain has the vision of countering aquaplaning, as it is one of the most dangerous situations for motorists all over the world, because aquaplaning is basically a grip loss caused by a layer of water between the vehicle tire and the road. So it's easy to understand that when a layer of water is between the tire, the wheel, and and the road, the car's driving behavior gets worse, and the motorist can't control the car. So it results in heavy and dangerous crashes. The problem is current safety systems like electronic stability control are not effective to win aquaplaning, as they can't have an impact on the tires. Well, I will say that these figures speak for themselves, as aquaplaning and wet road condition causes tens of thousands of deaths every year all over the world. So aquaplaning is a serious matter, and EasyRain is doing its part to come over it. EasyRain solution to aquaplaning is AIS, which stands for Aquaplaning Intelligent Solution. That is an active safety system which basically spray out fluid under pressure from 2 injectors placed ahead the front tires that break the water layer on the road, and helping the car and the driver to restore the control. Well, in this picture you can see the main components of AIS, which are two accumulators, 2 storage tanks where the fluid under pressure is stored, a pump, 2 injectors placed at the front tires, and the windshield fluid tank where the fluid under pressure comes from. AIS is a patented system, easy to fit into a serious vehicle, and it's also easy, and it's also modular, as car makers can build up their own configuration. AIS has been extensively tested on track, and has proven to reduce stopping distance by 20% in aquaplaning condition compared to vehicles that don't have it. So my general overview of AIS and EasyRain is over, and I'm well, passing the microphone to Michele.
Thank you, Paolo, for your introduction. I think it's very important to contextualize and see where simulation can be used. And it's a noble reason what you are investigating. And I think it's always interesting to see new approaches and new fields of application of our solution. My task today is to introduce the methodology that EasyRain is using, the computational methodology used. And this is a fluid dynamics meshless approach based on the software Particleworks. I will explain you what are the features of this software, the capabilities, both in terms of material modeling and also airflow integration. Of course, it's important to also account for air effects when analyzing external aerodynamics or vehicle interacting with external agents. Before then looking at the results of EasyRain, I will show you another interesting case study of tire improvement to reduce the splashing on the car body. So just to give you some other examples of the capabilities and the possibilities here. So as I mentioned, Particleworks is based on a meshless CFD approach that is called the moving particle simulation. This is a strategy to solve for the usual and conventional equation that we find in CFD, so Navier-Stokes and continuity equation. As compared to the conventional method that we see on the left at the bottom, we don't have with Particleworks to prepare a mesh, a static mesh, or an Eulerian mesh. So we can really speed up the simulation process because we can start from the CAD and we can start the simulation immediately. The Lagrangian approach basically will use the particles that the software automatically discretized at the beginning of the simulation as a dynamic mesh. And this approach is very suitable, of course, for free surface flow or splashing phenomena, like the examples we will discuss today. Yeah, as I mentioned, the CAD as is approach really speeds up the simulation process and allow us to use and take advantage of already present CAD drawings for also other application, not just design, but also improvements of the CAD itself. Moreover, the fact that we don't have to generate a mesh allow us to speed up the simulation such that previously workflow that took more than weeks are now achieved in just days. So in this way, we can create a digital prototype of our product, and we can analyze and improve it without the need of a physical testing or physical on track, in this case, testing. Here we will see some examples or features of the software. On the left, we have a snow modeling allowed that is enabled by a DEM solver that is also integrated in Particleworks. So we are talking about solid-like or powder-like material. On the right, we have a highly viscous flow of mud interacting with a car body, so a typical soiling application, and we can clearly see mud accumulating on the car body, interacting with the tires and spreading all over. So those are some visualization of the capabilities. And then, as I mentioned, it's important to integrate air. We can do it in different ways, either importing a pre-calculated air field, like from ANSYS Fluent. We have an example above. So first we take our mesh-based external solver and we then import the air field to Particleworks, or another approach is actually to use an integrated and embedded finite volume method solver that is now available in Particleworks. So what you see on the bottom is the finite volume method in Particleworks that allow us to use the same simulation that we use maybe for the soiling and the wading analysis, also to integrate the air in a coupled way as well. So the MPS particles interacting with the finite volume, as we see also here in the two videos. We have the modeling, we model together the MPS fluid phase and the finite volume air phase interacting with each other. Regarding case studies or a more, let's say, insightful example, we can discuss about this interesting presentation from Sunao Tokura, Promethex Software. He presented at the latest NAFEMS World Conference this presentation that I will just give you some insights of. And the topic was to optimize the tire shape in order to reduce the interaction between a splashing paddle and a car body. So the idea was to minimize what we see on the left in red, so the water interaction. That's a map of all the areas that are touched by water, splashed by the tire. And the idea was to investigate and let's say screen between different tire configurations in order to minimize that area. So here we have an example of three geometrical features of the thread. We can see that the groove length and the location was changed and there was an analysis on how the wetted area could change after those improvements or modifications. And we can see that actually they were able to reduce by 14% the total wetted area on the car body, at the bottom of the car body. So this can improve safety, but also reduce, let's say, fuel consumption or other aspects. Here in the video, we see clearly the effect of the tire modification in terms of flow distribution ahead of the tire, but also in the discharge area at the back. Maybe we can stop the video at the end just to have a clear view. But if we can, otherwise we can see it.
I don't think so.
Yeah, never mind. So at the back, we can see that clearly we have much more water in the example with lower interaction with the car body. And also in the front and on the side, in general, you can visualize and you can qualitatively already understand that there is a clear flow distribution difference, and that results in the improvement I mentioned. That's it from my side. I will hand over to Silvestro for the main results and the application of Particleworks to the AIS system in EasyRain.
Okay, thank you, Michele, and thank you also, Paolo, for the introductions and for your parts. So I'm, as I told before, I'm Silvestro, and I'm the mechanical engineer working in EasyRain on this topic. Together with my colleague, Prasanna, we worked and we analyzed the results of the AIS system simulated by CFD. So from my side, I will, in my part, I will present the results of EasyRain from the CFD simulations. First, I will introduce the first prototype of EasyRain, and I will describe it from a more technical point of view. Then I will explain what was the objective of our simulations, what we wanted to show and to find out. I will describe more in detail the simulations. So what are we searching? What is our goal? Then I will give us a short insight on the vehicle model validation. So how we validated our model. Then I will explain the evolution of our system, but also the future optimizations. I will present, of course, the results and then the final conclusions. So first, let's start from our first prototype. EasyRain first prototype.
Sorry, Silvestro.
Yeah.
Just because in the chat they are mentioning that perhaps the microphone configuration or the audio right now it's a little bit problematic. I don't know.
Okay, that's a first. Okay,
Never experienced that problem before, so sorry for that.
Can you hear me now? I hope yes. I will go a bit slow, so maybe you can,
yes.
interrupt me if it's the case.
Sorry for interrupting you.
No problem, no problem. Of course. So, first history lesson. This was our first AIS A1 prototype. This was a project where this system worked under the principle of instant pressure generation, meaning that water coming from the windshield washer tank was aspirated by the pump, and it was compressed thanks to the cylinder pump. The cylinder pump was activated by an electric motor, and it was controlled by a motor brake. Then the pressurized fuel was sent to the valves. Then, when the valves were activated, the nozzles were directed the fluid in front of the tires, as we explained previously. So, why are we simulating? So this first prototype was intensively studied and developed based on test track experiments. These test tracks are costly, but also really time consuming. So the need for an alternative arose. So as a solution, we used Particleworks CFD simulation to study, develop, and optimize the AIS system. With the simulations, we tried to replicate the same condition of the track test, meaning velocity, but also water layer depth. What are we simulating? So the objective of our simulations was to replicate the conditions that we found during a test track in full aquaplaning conditions. These conditions include a controlled pool filled with a known depth of water, a vehicle speed which is well above the normal aquaplaning conditions, meaning above 90 kilometers per hour, a long paddle, usually it's way longer than 75 meters, but also we included the aerodynamic effects of the air. So as you can see in the picture, the picture on the right is a picture taken from a real test track where we experimented our system. So regarding the injection system, when we did our simulations, particular attention was given to the jet, which is the main focus of the system. Mainly, we studied the position, the inclination, the shape of the jet, but also the flow rate, which is strictly related to the injection pressure. Okay, so once we proven that the feasibility of the track test of the simulation for the track test condition, we validated the simulation setup in order to be confident in our results. So how we did it? We did it in two ways. First, we did some experimental tests with a load cell. A load cell is an instrument which measures the impact force of a jet. Then we replicated the same conditions in the CFD environment. So, and we measured as well the forces at the impact. Also, we chosen a track test as a reference, and which was in aquaplaning conditions, and we replicated it in the CFD. We tried to find a correlation between these results, so the jet force and also the track test. So as I said, the load cell is an instrument that we used to measure the force of the jet. We did various experiments, but also various simulations in order to see if the CFD was able to capture the trend of the force that we measured. So on the left, you can see the experimental force, the trend of the force that we found with different heights of the injection, so height from the ground. On the right, we replicated the same conditions with the CFD, knowing the injection pressure. We saw that the CFD software is able to capture with high accuracy the trend of the force, and also it's able to capture the difference that we have when we vary the height. Also, we did a sensitivity analysis to measure the effect of the particle size on the simulations, and we saw that the results were really good. Okay, so reference case. After we validated our model, so after we felt confident with the results provided by the model, we chosen a track test where we knew that the car without this system, so without the AIS system, would go in full aquaplaning conditions. So complete loss of the control. Then the same condition was replicated with the AIS system on, and we saw that we were able to regain traction of the car and control of the car. So we simulated this track test and we put it out as our benchmark against which we compared our future simulations. So aquaplaning, as my colleague said, aquaplaning is defined as the capability of the as the limit above which the tire is not able to evacuate the water anymore. So it's a condition where the car floats basically on the water, losing all the control. This phenomena is highly correlated with the water layer. So it plays a big role in the aquaplaning effect, but also the vehicle velocity. We have also other parameters such as car weight or the consumption of the tires, but those were kept aside. AIS system is able to clear the part of the water in front of the tire, mainly in the center of the tire where the aquaplaning phenomena starts. Okay, so simulations of the same conditions were made, allowing to analyze in detail what is happening in front of the tire, so the most critical part. On the bottom, we can see the results from let's say, real conditions. So when we go in aquaplaning without AIS system, we are not able to steer or to avoid a possible obstacle. With the AIS system, we are able to control the vehicle and safely avoid any obstacle. So as I said, the reference case was tested. So in the simulation, we replicated the same conditions as the real car. So meaning flow rate, water pressure, position and orientation of the jet, velocity of the vehicle, but also aerodynamic flow. With advanced post-processing, we analyzed these results in order to understand what was the most critical parameter for our study. What we studied during our post-processing. Mainly, we concentrated on two parameters. One was the quantity of water which was cleared in front of the tire. So we chose control volume in front of the tire, and in there we measured the quantity of water flowing through that control volume during the system activation. Of course, less water flowing means a better efficiency of the AIS system. On the right, you can see the opening of the water, because the higher the opening, the faster the vehicle is going out of the aquaplaning system. So for us, these two were a good indication of the efficiency of the system. Okay, here I'm showing a small overview of our simulations. So as I said, we have our vehicle, which is an Audi, which we did all our experimental tests. On this vehicle, we did the experimental testing with the AIS Proto A1 that I presented before, and we created our reference case. Then internally we developed, we improved the AIS Proto A1 system, and so the AIS Proto A2 was born. With this system, we know the characteristics of this system, and we tested it on the first vehicle, so which is our Audi, but also on a secondary vehicle. On this secondary vehicle, we only tested AIS Proto A2 because it will only be this system will be the only one which will be mounted effectively on the vehicle. Okay, so for technical reasons, the first prototype changed. We improved it internally. We did a great job changing the system, improving it, and making it a lot smaller, but also a lot more effective. This new prototype is still under production as we speak, so everything is under production. But we know that it will have the characteristics that we are showing. So if we take a look at the pressure of the fluid, we can see that with the first prototype, we had, first of all, a shorter time of activation. So we have less time of injection. And also an average, pressure average, which is a lot lower. The second system has a different working principle, and the most important thing is that it manages to spray more with a higher pressure. Okay, small overview on the second prototype. It works under the principle of pressure storage, so the two accumulators, and we have a smaller motor and a smaller pump, but also a lot more efficient. So first of all, based on the new performances of this new AIS system, an improvement is highly expected and foreseen. So by doing the simulations on this new system, we compared it against the first one, and we saw that we have an improvement of about 25% on the quantity of water cleared in front of the tire. You can see it clearly from the images, but also if we measure the volume of water flowing through the control volume, we see that we have a good improvement. As I told you, we have two vehicles. So first, we studied our Audi. We studied the effects of AIS-1 and also AIS-2. But then we have yet another vehicle that we will announce in the future, which has completely different settings. So it has a different impact point of the jet. So it has an impact point of the jet which is further away from the wheel center, and also the jet is higher. And we studied this new system. With this new system, we saw that we have different results, but here the question arose: what if we have the liberty to move our injector and to move our impact points and impact angles? So we did a study on the effects that we would have. Firstly, if we maintain the impact point constant, so with the liberty of moving the injector in the longitudinal axis of the vehicle. And we saw that we have a strange, we have a trend of in this case of the opening of the water in front of the tire. We see that by increasing the jet angle, so by moving the injector backwards, we have at first an improvement, but then a decrease in the performance. This was a good indication about the effect of the angle in the performance. Then another study was made in another condition. So what if we have the constraint of the packaging, like is the case in our present, where we need to keep the injector fixed. What will happen if we have a vertical jet or an inclined jet? And from this, it seems that inclining the more that we incline the jet, the better efficiency of the system we have. So this gives a great help to us in choosing how to install this system and how to also maybe talk with the car makers and maybe reserve the space on the vehicle, let's say in a future production mindset. So this was a really important result for us, because it gave us the idea of what we should do in the future. Because since until now we only worked on serious vehicles which had limited space, and we had almost no liberty of moving around inside the car. For future applications, we hope that this can be a good help for us. So to do a summary of what we did, we tested for the vehicle 1 both systems. So we chose as a reference the AIS Proto A1 system that we know that we tested on the track. On the same vehicle with the same settings, we installed the AIS, we simulated the AIS Proto A2, and we measured what would happen. And it seems that we will have an improvement of around 25%. Then we also considered the second vehicle where we installed directly the Proto A2, and we saw that if we compared it with the reference case, we would have again a 25% improvement. But if we start to think ahead and optimize this system, we see that we could have potentially a 35% increase from the reference case, which is for us a great achievement. And I don't think that without the study together with EnginSoft, so by using the particle CFD simulation, we would have known this so in advance. Now, as I told you, the system is under production, and we are planning already the test on the track. So we hope that all these results will be confirmed by track tests, and from there, I think we will have a great, a lot more confidence in the system and in our studies. So, as I told, the collaboration between EasyRain and EnginSoft was concentrated on the modeling of the first active anti-aquaplaning system by using the meshless moving particle simulation. Those AIS systems were virtually analyzed and correlated lab and on-track results. And as I told you, by means of Particleworks, virtual testing of a new class of vehicles has been possible with promising results. So now we just have to wait and see what will happen on the track. This is all from my side, and please, if you have any questions, I will gladly answer.
Okay, I guess there are no questions.
There are no questions. I've been clear enough. Is it still working?
Michele, can you hear us?
I actually think there are two questions.
Okay.
Okay.
Yeah, they just came in when you said that there were no.
Okay. Please.
So should I read them for you? Okay. Alex Riedman asks how much work have you done to optimize for vehicle soiling? So if you also look at that.
But you mean it's a question for us, right?
Yes. So I guess Alex wants to know if you also look at soiling, or let's say
so
interaction with other parts of the vehicle. Yeah.
Okay, so no, we didn't do any work on that, because of course our main for us this work was more concentrated on if the system will work and if the system will work better. So no, we didn't do any work on that, but from what we saw also experimentally, the water seems to go away from the car, so externally and in the front of the car, with no, the water that you can see on the left in this image, that one would come also with the system off. With the system on, the water is flowing in a frontal direction. Mm-hmm. But we never did this study.
Okay, and then Andre Van Dam and Massimo Galbiati ask actually the same question. So about what is the average simulation time, or how long did the simulation take?
Okay, for that I think I have a slide. I don't remember on the top of my head. It should be around 40 hours per simulated second. Yeah, keep in mind that we are simulating around 7 million of particles. So yeah, it's 40 hours per simulated second. by using a I don't have an NVIDIA GPU.
3090, right? RTX 3090 should be.
Exactly.
And here we are dealing with an implicit method for the pressure solver. So that's why also I think the simulation time could increase a little bit because of course we needed to compute very precisely the pressure distribution in the jet and in the interaction with the paddle. So the comment from Alex Riedman from EnginSoft UK is that you could, let's say, increase the applicability of the system if you market it as, or you pitch it, not just as an aquaplaning maybe solution, but also with the anti-AIS sensor for soiling prevention. So to also reduce contamination, maybe you could apply a similar system. That's the comment from Alex Riedman. You could.
Wait, you mean cleaning the ADAS sensors?
Yes, I guess.
Okay, if that's the case, we didn't present it, of course, but we are already working on that. So we are already studying this system as well. Our vehicles will have these features. So our prototypes will have the feature of ADAS cleaning.
Okay, interesting to know.
This was not the case. We didn't think that this was the case, but yeah, we are working on that as well.
So we have more questions. Matthew Savage asks about this aspect. So let's say you optimize your system. What is your planning in terms of other tests or simulation that you want to analyze? Again, soiling could be a possibility, but do you have other things in mind?
Yes, I mean, experimental testing, that's a completely different case. I mean, we want first, our objective now is to confirm these performances. So we want to absolutely confirm that this second generation AIS system is better than the first one. And this for us would be the first objective. Then I think that the next improvements would be to optimize the pressure and to see what would happen maybe with lower pressure or maybe different ways to apply the jet, different shapes of the jet, and also flow rates. Anyway, anything that is related to maybe water consumption, because that's also an issue. I mean, you can imagine that we cannot spray infinitely, so we need to optimize as much as possible the water injections. But also we are working internally to develop a new class of injectors, so that one will also be a good use for this Particleworks system.
Okay. I do see a lot of new questions coming up. We still have time, so I think it's interesting to continue the discussion. John Forsgren asks about if we can provide correlations between a test and simulation in terms of behavior of water. I don't fully understand the question, like in terms of what type of application, either not just soiling or external aerodynamic, or I mean, here we have an example of also visual validation because EasyRain compared the
Yeah.
the flow, right?
Yeah, so I could give you an example on this, and maybe this is what you say. If you can see from this video, you can see that there is some water coming from the wheel hitting the jet, right? This is for us. It's an important issue, and we also saw it experimentally. So basically, the wheel is pushing quantities of water from forward hitting the jet. So that for us is it is validated. I mean, this is happening on the simulations and in real time. We want to go deeper into this topic, and we want to do it. Of course, testing is expensive. Everything is a bit, it's not as easy as it may seem. Also, we organized some time ago. We organized a trip on a test track which had the possibility to film the puddle from beneath and to see what happens what happens to the jet and also to the puddle. Unfortunately, there has been some issue, and we need to reschedule this type of test.
Okay, thank you. So of course, maybe you could also design a cover for your system if you see this type of interaction, or in general, you can discuss maybe with the tire manufacturer.
It's already in place. Everything is happening. It's a correct thought, but it's already happening.
Yes, I guess that simulation results really can guide you in different directions.
Yeah, for sure.
So a couple more questions. So how do you measure the stability of the car during the test in order to understand that Proto A2 is better than Proto A1?
Okay, so what we usually do is we go on a test track and we measure. So imagine you're driving in this really long puddle, and when you're in aquaplaning condition, whether you steer right or left, the car goes with its momentum, so it goes in a straight line. And if you measure the lateral acceleration, you would see that you are around 0 lateral acceleration, 0 meters per second squared. With AIS system, when we activate, we are able to do the maneuver of steering right and left. Of course, we don't have the lateral acceleration that we would have in dry conditions, but we are able to steer, and we are able to, as I told, to avoid an obstacle. So that's a really good measuring for us. But also we have the tests on a curve where the car in aquaplaning conditions, so it's a wet curve. So the car goes in aquaplaning while steering, and without the system, you go basically you go in a tangential direction to the curve. With a system, we are managing to do the curve, and to we don't get out of the street. So
okay.
We have our series of tests of unified testing.
Perfect. Last question, I think. So, by the way, Alex asks if we will be able to provide the recording of the webinar. Yes, the webinar will be recorded and shared. So, Paolo Lorusso asks about the post-processing of the results. Maybe I can address that. So the question is there an EnginSoft software, or you can use other software to do the post-processing? So what was shown here was done inside Particleworks, the software we provide from EnginSoft in collaboration with Promethex software. We have in this software different ways of post-processing. So really surface rendering, creating videos, creating pressure maps or wetted surface areas. So all the basics post-processing that you can do in a traditional CFD, you can also find them in Particleworks. What you can also do is to export the results in ParaView, maybe, or you can also create renders of the results in Blender. So there are tools that allow you to transfer the simulation results to other post-processing or digital animator softwares. Yes. Okay. I hope this was clear for everyone, and I would like to thank you all for the question, for the interesting, for your interest. And I would like again to thank EasyRain, Paolo, Silvestro, and the collaborators for this very insightful and complete work between simulation and real cases, real life, let's say, issues and also solutions. So yeah.
Thank you.
I don't know if you.
Thank you, Michele, and thank you, EnginSoft, and thank you, all of you guys, for joining the webinar.
And also thank you, Michele, for all your support. It was really, was really appreciated.
Yeah. Good. So again, thanks you all, and we will provide you in the future the webinar recording if you are interested in.
Okay. Goodbye,
Bye,
everyone, and have a nice evening.
Yeah. Bye.
Bye. Bye. Bye.